Welcome back, class. So earlier we have learned about the inverting amplifiers, non-inverting amplifiers, and applications of the inverting and non-inverting amplifiers. For example, summer circuit, voltage follower. Okay. Now we are going to learn about the more applications of the op-amp amplifier. So the first one is current to voltage converter. So typically when we talk about the photodiodes or solar cells, solar panel, the output of the solar panels is basically the current. Okay, and when you want to charge the battery, okay, so that current will go to the load and it will charge the battery. So if you want to convert that current to voltage for the handling in the circuits, so we can use the op amp for that. Okay, so for example, this circuit is actually representing the photodiode or solar cell, and the output is the current. Okay, so if you just replace, for example, a non-inverting amplifier here. Okay, so here, so basically this is 0 volt, so virtual ground, this will be 0 volt. So okay, so this is the input incoming current I1. So basically here I1 will be equal to I2. Okay, this whole current will goes here, and we know that basically the I1 is the input current from this solar cell, and I2 we can write as 0 minus output voltage divided by the feedback resistor, or output voltage will be minus input current multiplied with the feedback resistors. Okay, so basically the input current is converted to the output voltage. Okay, so here your output voltage is proportional to your input current. So we can convert the input current to the voltage. Okay, so as the input current increases or decreases, your output voltage value will be increasing or decreasing with the just 180 degree phase shift because of this negative sign. So this is one application. Another application is voltage to current converter. Okay, so this is very simple. Okay, so let's say the simplest circuit is that you have an for example non-inverting amplifier. Let's take the inverting amplifier, and this is my input, and we know that this is the feedback resistor. So basically here we have the let's say this is R2, this is R1, and here we are supplying the input voltage. Okay, and this is our output current, and so here we are having the I2, this is I1. Okay, so basically we know very well that basically I1 is equal to I2. Okay, in this case, and we know that I1 is basically V input minus 0 divided by R1, and I2 is basically 0 minus V naught divided by R2, right? Or what we can do here, so here we notice one thing. Okay, that basically if we write this like this, so we can notice one thing, that basically this current output current is proportional to the input voltage. Okay, so here for example if you install your sensor or something like that, okay, so the current which is flowing through that sensor, it is actually depending on the input voltage. Okay, so we can convert the voltage, input voltage, to the current, and we can control that circuit. So this is the simplest form of the voltage to current converter. Okay, but its drawback is it requires one terminal to be grounded. For example, this terminal to be grounded. Okay, so but in some real circuits it becomes difficult to ground the circuit, and for that case what we do, we use this modified circuit. So here the positive terminal is not grounded. We have the feedback network, we have a resistor which is connected with this positive terminal, and we have a load, okay, which is coming here, and we have another resistor which is connected here. Okay, so here if we apply the same rules, okay, for the first one is we know that I1 will be equal to I2. Okay, and we know that this load voltage, it will be IL into load voltage will be IL multiplied with ZL. This will be our first equation, and I1 is equal to I2. So we know that I1 is what? So here we have VL. Okay, and at this point we also have VL. So it means at this point we also have VL. So here if we have VL, it means here we also have VL. Okay, so this is just the derivation. So V1, the I1 will be V1 minus VL divided by R1, and output will be VL minus V0 divided by RF, that will be I2. Okay, and also we can notice that here these currents, okay, IL and plus I4, these are basically the I3. So this incoming current is going here and here. So I3 is basically equal to IR plus I4. So if we just remanipulate all these equations, so finally what we can get, basically the load current, okay, this formula is the ratio of the feedback resistance divided by R1 into R3, okay, multiply with the input voltage. Okay, so depending on the input voltage, okay, we can control the load current. Okay, so this is a voltage to current converter. So the next very important application, okay, is the difference amplifier. Okay, so far we have learned inverting amplifier, non-inverting amplifier. Okay, so we learned about the summer amplifier. Okay, we can design the sum application. So we can also design the difference amplifier. Okay, so basically in difference amplifier, what is happening, that difference amplifier will give us the output in the form of the difference of the input. Okay, for example, here the output is the difference of this input V2 minus V1 multiply with the sum factor, okay, K. So we can get the difference of the input signals by using this amplifier. Okay, so to find this factor K, what we can do, we can do some simplifications. First is we consider these circuits into two, we divide this circuit into two. Okay, for example, first we consider the inverting case. Okay, so we supply the input here, and second terminal we make it ground. Okay, so the positive terminal is grounded. Okay, so in this case we know that our output voltage, it will be ratio of the feedback resistance divided by input resistance multiply with the V1. Okay, we know very well. Okay, and second case is non-inverting case. So here we have the input, we make this ground. Okay, so in this case we know that what is our output voltage. If you remember the non-inverting case, that the output voltage is the 1 plus R2 over R1 multiply with the input voltage. So usually we apply the input voltage here, multiply with the input voltage. Okay, so here we are actually getting the divider network. So here basically this input voltage here is the voltage drop across the resistance. So R4 divided by the total resistance multiply with the actual input voltage. Okay, so this will be actual our voltage here. Okay, and our final output voltage, it will be the summation of the first voltage plus this second voltage. Okay, now here if we do some simplifications, okay, with some simplification what we can get, okay, we can get like this is the first one from here, this is from here, actual output voltage is summation of this. So if we just put these numbers here, we will get this equation. Okay, but if we talk about the ideal difference amplifier, okay, if we talk about the ideal difference amplifier, okay, for example, let's assume that the both inputs are same. So in that case output will be 0, because output is the difference of the input voltages. So if both inputs are same, then output will be 0. So if you put these conditions here, so basically it will become 0. So this term will be equal to this term. Okay. Now to make these two terms equal, okay, what we can do, the ratios, these two ratios, okay, R4 over R3 should be equal to R2 over R1. Okay. So the ratio of R4 over R3 should be equal to R2 over R1. If these two ratios are met, then basically this term will be equal to this term, and only in that case we could have this relationship that they both are same and their difference is 0. So to make these two terms same, what we have to do, we have to make the ratio of the R4 over R3 is equal to R2 over R1. So once we do that, after we can derive this final relationship that the output voltage is the ratio of the R2 over R1 with the difference of the input V12 minus V1, or output voltage is the difference of the input voltage multiplied with the ratio of the R4 over R3. So either you can take the ratio of this or ratio of this. The results will be same. So these are our final formulas. So in the difference amplifiers, the main things which has to be understand, okay, that the ratios of these two resistance should be the same. So if you are designing the difference amplifier, make sure that this relationship is met. Okay. Example we will solve in the live session. Okay. So in the difference amplifier, the most important thing is that this should be met. Okay. So if you look at the input side, okay, so basically like if you talk about the input resistance from here, so basically that will be only this resistance. And if you talk about the input resistance from the second terminal, so that will be basically the sum of these two because they are in series. Okay. So and the most important thing is their ratio should be same. Okay, but one very important thing is here, what will be the differential input resistance. Okay, so this is the input resistance for only this circuit, this is input resistance for only this circuit. So what will be the differential input resistance for both cases? So basically a differential input resistance can be derived using this formula, and this the final result is this one. I will explain that how we can actually derive this in the live session. Okay, so the differential input impedance, okay, is basically is equal to the 2 times of the R1, okay, by applying this relationship. Okay, so this is called differential input resistance. So we have made one assumption that in the ideal difference amplifier, if both inputs are same, output will be 0, and we have also made this assumption that the ratio of these two should be same. Okay, but in practical circuit, if this ratio is not same, it means or we don't have the same inputs. Okay, so basically in that case there will be some output, okay, due to the differences, and that is actually called the input common mode input signal. Okay, if they are not same, so there will be some common mode input signal, and the common mode input voltage we can calculate using this formula that we take the summation of 2 and divided with 2, and the common mode gain is basically the output over the common mode input voltage. Okay, and if we are talking about the ideal case, so ideally when the inputs are same, the output is 0, so the common mode gain will be 0. Okay, but in reality it could have some values. But the more important and the figure of merit for the difference amplifier is the common mode rejection ratio. Okay, so common mode rejection ratio, this is called common mode gain, and we have learned earlier on we have the differential mode gain. So the ratio of the differential mode gain divided by the common mode gain is called the common mode rejection ratio. Again, ideally it should be infinity. Why? Ideally we think that common mode gain is 0. So if this is 0, 1 over 0 will be infinity. In dB, just take 20 log of differential mode gain divided by the common mode gain. Okay, so these are the important figure of merit for the op-amp. One example, we will solve this in the live session. Another example is zero level detector. I will discuss in live session. Non-zero level detector, I will discuss these things in the live session. And also we could have other applications, the integrator and the differentiator, which we will see in the next lecture. Thank you very much for your time here.